So good evening, Sri Sai Ram. Okay, I'll share my slides now. Okay, actually, this is yes, yeah. I think two classes before. Uh, okay, when I'm explaining this example, okay, especially the second one, when x and a, actually here a is what? A is a set of all straight lines in the Euclidean plane. The relation S is defined by x and y are related by S if and only if x is perpendicular to y. Okay, here the relation S is not reflexive. Actually, I told that S is reflexive. Okay, initially I told reflexive, but not reflexive, and then later I told not uh, reflexive, but actually S is not reflexive. Okay, the reason is the given line is not perpendicular to itself, so that's why S is not reflexive. And in fact, this is what? Irreflexive. Because irreflexive means what? A is not related to A for every A. So that's why we know that if you take any line, it's not perpendicular to itself. So that's why A is not related to A. So this is and hence this is what? Not, this is irreflexive. So the relation S is not reflexive, but it is what? Irreflexive. And symmetry. Why it is symmetry means x is perpendicular to y implies what? Y is perpendicular to x. But it is not transitive. Not transitive. The reason is x is perpendicular to y, y is perpendicular to z, but x is need not be perpendicular to what? Z. Voice is breaking. Okay. So I don't know exactly. Thank you for your message. Uh, Maybe due to network issue. What about now? Is it fine? Still you have problem. Okay, just I'll continue. Suppose if you have any problem, please mention again. Yes, and in the last class I explained up to I think I explained the first example. So just I don't know exactly whether I explained this example or not. Okay. So again, I will explain this the problem. I'll start from this problem. Prove that the relation congruence modulo m over the set of positive integers is an equivalence relation. Okay, here n, capital N, be the set of all positive integers, and m be a given positive integer. So now we define a congruence modulo m. This is the relation congruence modulo m relation on n as follows. So how we are defining x comma y belongs to n. N is what? Set of all positive integer. So x is congruent to, this is the congruent symbol, congruent to y modulo m or mod m if and only if the difference x minus y is divisible by m. So this is the relation. Okay, if x minus y is divisible by m means what? X minus y is equal to some k into m for some integer k belongs to z. So the k is what? Belongs to integer means k is either positive integer or a negative integer. Okay, now I'll take three elements x comma y comma z belongs to capital N. I want to prove the relation is reflexive. To prove the relation is reflexive, I need to prove x is congruent to x mod m. Okay, wow. So to prove x is congruent to x mod m, I need to prove what? X minus x is divisible by m. So that's why I'm going to calculate x minus x. X minus x is equal to 0. You can write 0 is what? 0 into m. And hence x minus x is what? Divisible by m. X minus x is divisible by m. That's why we can write x is congruent to x mod m. This is true for all x belongs to capital N. So that's the relation. This relation is what? Reflexive. Next, symmetry. If x is congruent to y mod m, then I need to prove y is congruent to x mod m. If x is congruent to y mod m, implies x minus y is what? Divisible by m. So if x minus y is divisible by m, you can write x minus y is equal to some k into m for some integer k. So from this you can write y minus x is equal to minus k into m. So the next step you can write one more step here. So y minus x is equal to minus km implies y minus x is divisible by m. So if y minus x is divisible by m, y is congruent to x mod m. So that's all. So the relation is what? Symmetric. So the next one, transitive. If x is congruent to y mod m and y is congruent to z mod m, I need to prove x is congruent to z mod m. So x is congruent to y mod m implies x minus y is what? Divisible by m, and hence x minus y is equal to some k into m. Similarly, y is congruent to z mod m implies y minus z is divisible by m, and hence you can write y minus z equal to some l into m for some integers k and l. Now if you add x minus y and y minus z, left hand side, the right hand side is what? K plus l into m. So y gets cancelled. X minus z equal to k plus l into m. So k and l are integer, means k plus l is also what? Is an integer, and hence x is congruent to. So this implies next step we can write x minus z is what? Divisible by m. So x minus z is divisible by m, and hence x is congruent to z mod m. So, and hence the relation is what? Transitive. So and hence the relation congruence modulo m over what? Over set of positive integers is an equivalence relation. Okay, second problem. Let capital R denote a relation on the set of all ordered pairs of positive integers by x comma y, okay, related to u comma v, if and only if x into y, x into v, first element into second element is equal to second element into first element. So x first element, here v is what? Second element. Product of first and second is equal to product of second and what? First. So okay, now I want to prove this is an equivalence relation. So here first I need to prove what? X comma x is related to x comma y is related to what? X comma y. So I want to prove reflexive. So that means I want to prove what? X comma y is what? Related to x comma y. So if I prove this one, then R is what? Reflexive. So to prove this one, what I need to prove? Okay, wow. So I need to prove first into last. Okay, wow. First into last. First into second. X into y is equal to second into first. Second into first. So y into x. I should prove. But this is true in general. Okay, xy is equal to yx for every x comma y belongs to where? What is your set? Set of all positive integers. Okay, set of all positive integers for every x comma y belongs to is set of all positive integers. This is true for every x comma y belongs to z plus, and hence you can write what x comma y is related to x comma x. Okay, so because this is true in general. Next, so next actually I want to prove symmetry. Okay, symmetry I'll take. So x comma y is related to what? U comma y, u comma v. If I take like this, so finally I need to prove what? U comma v is related to what? X comma y. So from this, what we have first into second. So that is x into v equal to second into first, y into u. Now, okay, I think up to this you got it. Now, here, suppose I don't know what I need to proceed further. Okay, maybe I'll write here x comma y. Okay, or x comma y. I'll write in the next page x comma y related to what? U comma v. Finally, I need to prove what? U comma v related to x comma y. So this implies, okay, this implies what you have first into last equal to second into first. X into v equal to y into u. So I want to prove this one. Okay, what is the meaning of this? First into last, okay, u into what? Y is equal to second into what? First, v into x. So from this, I need to derive this one. Okay. So look at here. I can write the next step. Y into u is equal to x into v. Next step from here to here, you can write this step. Okay. You can write uy. Similarly, you can write what? Xv, you can write vx, and then you can write that's all over. So and hence the relation is what? Symmetry. So next transitive. Transitive, they will take here x, y, u, v, okay, mn are all positive integers. So because that is your set in the problem, it is given. So next step, if x comma y is related to u comma v means first into second xv, second into what? First yu. Similarly, u comma v related to what? M comma n. So u into n is equal to what? V into m. Now multiply the left hand side. So xv into what? Un equal to right hand side is what? Yu into vm. Now we know that u and v are non-zero. Okay, so if u and v are zero means nothing to prove. Okay, so 0 equal to 0. So, okay, so similarly 0 equal to 0, there is nothing to prove. So you should assume u and v are not equal to 0. That's why u is not equal to 0. Then that's why we are cancelling what? Vu or uv both side. So after cancelling uv, what you will get? Xn is equal to what? Ym. So now actually what I need, we need to prove x comma y is related to what? M comma n. Okay, now I'm going to check whether these two are equivalent. That means from the relation defined by the problem. So I have this one. I need to prove this one. So x first into last. Okay, xn is here is equal to second into first. Okay, now you can write this one is like this. this one. Similarly, you can write this expression is what, like this. So and hence R is what, transitive, and hence the relation R is equivalence relation. Okay, the next problem is let a relation R be defined on the set of integers, set of all real numbers. Okay, real numbers. If x and y, I think y is missing here. If x and y are real numbers, okay, x is related to y, if and only if x minus y is what, is a rational number. Okay, show that this relation R is what, equivalence relation. So first I need to prove x is related to x. So that means I need to prove what, x minus x is equal to x minus x is a rational number. So as we know that x is equal to, sorry, x minus x is equal to 0, 0 is a rational numbers for all real numbers x. So and hence we can write x is related to what, x, and hence R is reflexive. Second one, symmetric. X is related to y. I should assume, finally I should prove what, y is related to x. If x is related to y, you can write x minus y is equal to some z, where z is what, z is a rational number. Now y minus x is equal to what, minus z. When z is a rational number, minus z is also what, rational numbers. So and hence y is related to what, x. So and hence R is what, symmetry. Similarly, next transitive, x is related to y and y is related to z. X is related to y implies x minus y, here this is equal to R1, and y minus z here equal to is not visible, equal to R2 for some rational numbers. R1 and R2 are what, rational numbers. Now you can add both the left hand side as well as right hand side. So x minus y plus y minus z. Okay, x minus y plus y minus z equal to R1 plus R2. So we know that R1 and R2 are rational numbers. So from this you have x minus z equal to R1 plus R2. So and hence this is a rational number, and hence x is related to what, z. So and hence R is what, transitive. So we proved it is reflexive, symmetric, and transitive, and hence this relation is what, equivalence relation. Okay. Now the next problem is here. Let capital L be the set of all straight lines in the Euclidean plane, and R be the relation in capital L defined by if x is related to y, if and only if x is perpendicular to y. So I think today class, when I started this class, I discussed this one, but slightly this is different from slightly. Okay, well, the question is R is reflexive. It is not reflexive because x is not perpendicular to what, x. It is not reflexive, and it is symmetric. Yes, it is symmetric. Why it is symmetric? If x is perpendicular to y, then y is also perpendicular to what, x. Okay, next transitive. It is not transitive because x is perpendicular to y and y is perpendicular to z. Need not be imply x is perpendicular to z. Whether it is antisymmetric, it is not antisymmetric. Why it is not antisymmetric means, I'll write here. For antisymmetric, you should take two different elements. Okay, x not equal to y. This is one of the definition. There are two equivalent definition. X is related to y. Okay, whenever x is related to y. Here the relation is what? The line x is perpendicular to what? Y. So okay, so I'll put a line like this. Okay, and this line is not to distinguish these two. Okay, So I need to prove, okay, this is the first one is, this is a definition. Okay, here x comma r, you can write this one instead of x related to y, x comma y belongs to r. So x comma y belongs to r. So that means what? X is related to y. I need to prove what? X comma y is not in r, not in y comma x. Sorry, y comma x, y comma x not in r. Then we say that it is what? Antisymmetric. So I'll take two lines, x and y, two different lines. So x is perpendicular to y, implies actually what? Y is perpendicular to what? We know that x. So actually here x comma y are what? Two different lines. X is related to y, but finally you are getting what? Y is also what? Related to what? X. But as per the definition, y is not related to x. So that's why this relation is what? Is not symmetric. Antisymmetric. It is not antisymmetric. It is only what? Symmetric. So next, give one example of a relation R on A is equal to set A 1, 2, 3,
Sir,
4. Yes.
can we use that second definition and prove that it is not an antisymmetric?
Second definition. Second
Yes, sir.
definition is okay. Actually, for second definition, little bit difficult. That's why, because x is perpendicular to y and y is okay. So okay, you can say yes, x is perpendicular to y. Okay, what? And what? Y is perpendicular to x implies it should be what? X is perpendicular to y and y is perpendicular to x, then we can't say it is x is equal to y. This implies what? X not equal to y தான் வரும். ஓகேவா?
Yes, sir.
ஓகேவா? So you can't say it is what? X is equal to y. This implies you are getting what? X is
Not
what?
an antisymmetric.
Not equal to y.
Okay, sir.
ஓகேவா? So
Okay, sir.
again, you are correct. Yes, actually, this is actually what? X is x comma y are what? Is related. You can write. This is the definition. Here what? Y comma x is what? Related. They are related. But I should prove x is equal to y to prove what? It is antisymmetric.
Yes, sir.
But here x is not equal to y, and hence it is what? Not antisymmetric.
Okay, sir.
Okay.
Understood.
Yes. Yes. Okay.
Thank you, sir.
Next, give one example of a relation R on A, which is neither symmetric nor antisymmetric. Okay, so I will show the answer. Neither symmetric nor antisymmetric. Okay, so I think the ninth one. So this is not symmetric. Why it is not symmetric? 2, 4 is here. 4, 2 is not here. Why it is not antisymmetric means for two different elements. Just why I told that 1, 2. Okay, wow. 1 is not equal to 2. 1, 2 is here. 2, 1 should not be here. Then only we say it is what? Antisymmetric. So 2, 1 is also here. That's why it is not antisymmetric. Okay. So next problem, give one example of a relation R on A equal to 1, 2, 3, 4. It's a set which is symmetry, transitive, but not reflexive. Okay, not reflexive you can easily give. Okay, one, because it contains 4 elements, 1, 2, 3, 4. 1, 1, 2, 2, 3, 3 is here, 4, 4 is not here. And also check it whether this is satisfies what? Symmetry and also what? Transitive. I leave it to you, you can check it. Okay, next one. This problem, let capital X is equal to 1, 2 up to 7, 1, 2, 3, 4 up to 7. Capital R is equal to set of all x comma y such that x minus y is what? Divisible by 3. Show that the relation R is what? Equivalence relation. So that's the first question. And then draw the diagram of the relation R. So actually, last class also, we discussed this problem, not the same problem. Actually, I shall show you this problem. Yes, here congruence modulo m. In that problem, congruence modulo instead of m you have what? 3. Here, what is your set? Set of all positive integers. There your set is what? 1 to 7. So and hence that problem is a particular case of what? This problem. I explained this problem twice. Last class also, this class also. That's why I leave it because this is a particular case of that problem. You can show that a set to x together with this relation. Here x minus y is divisible by 3. Okay, x minus y divisible by 3 means what? X is congruent to y mod 3. So that is a meaning. Okay, wow. So first step, reflex how to prove. X minus x is equal to what? 0. You can write 0 is equal to 0 into 3. So and hence x minus x is what? Divisible by 3. So x is related to x. Okay, reflex is over. Next symmetry. Assume x is related to y. That implies what? X minus y is divisible by 3. So x minus y is divisible by 3 now. Okay, wow. So you can write x minus y is equal to what? Some some m into, k into 3. K into 3. From this you can write y minus x is equal to what? Minus k into 3. So and hence y minus x is what? Divisible by 3. So very similar proof. Okay, second part, how to show that, how to draw the diagram of R. The diagram of R is nothing but, okay, you have 1 to 7 set. Okay, here look at look at this one first. 2 and 5. So 2 and 5 are the difference is what? The difference is 3, which is divisible by 3. Okay, so that's why 2 and 3 5 are in, I will take separately. So this is a vertex. Okay, this dot is what? 2 represent, this dot represent what? 5. Similarly 5 minus 2 is divisible by 3. That's why the arrow is from here to here, 5 to 2 direction. Similarly 2 minus 5 is what? Minus 3. That is also divisible by 3. That's why you have the arrow from here to here. And self loop, because 2 minus 2 is equal to 0, so that is divisible by 3. So similarly there is a self loop like this, because 5 minus 5 is what? Is equal to 0, which is divisible by 3. So you cannot combine these two elements here in the element what with 1, 4, 7 or 3 and 6. Okay, similarly because for 2 and 3 what is the difference? Only 1. For 2 and 4 the difference is 2 and 6. What is the difference? 4. That is not divisible by 3. For 3 and 6 again the same idea is 6 minus 3 or 3 minus 6 is divisible by what? 3. So that's why you have the arrow both sides, and 3 minus 3 is equal to 0, that is divisible by 3. So that's why self loop here also, here also. Similarly 1, 4, 7. Okay, so 1, 4, 7. So the difference, okay, either 1 minus 7 or 7 minus 1 is divisible by what? 3. So that's why I have the arrow from 1 to 7, from similarly what? 7 to 1, both way. Similarly 4 and 7, if you take, is 4 minus 7 or 7 minus 4 is what? Divisible by 3. That's why I have arrow two sides. Similarly for 1 and 4. And also for self loop you can put it. So this is the diagram of R. Okay, so actually this one is the continuation of, okay, actually yes, I think I wrongly put there. So actually for the fifth problem, subdivision 1, 2, 3, 4, 5, 6. Okay, 6 is here. 7th one, it went here. 7 and 8 is here. So this is the relation symmetric, transitive, but not reflexive. Why it is not reflexive? Because the A contains what? 1, 2, 3, 4. So 4, 4 is not here. So this is an example for equivalence relation. You can check it. 1, 1, 1, 2, 2, 3, 3, 4, 4 is here. And 1, 2, 2, 1. So symmetry is also here. And also transitive, you can check it. Okay. Okay. Sorry. The next problem is okay. So in this slides you can see. Okay. So actually in the example 5.9, I will show you. Actually here I think there are two subdivisions, 1 and 2. So the first subdivision already we discussed. I will show you where we discussed. R is a relation on a set of ordered pairs of positive integers such that a comma b comma c comma d in R whenever AD equal to BC. So show that R is what? An equivalence relation. Just now I told that the first element into what? The second element is equal to second element into what? First element. Okay, here you have ABCD. There you have instead of ABCD, UV, I think so. Okay, look at this one. Yeah, XY, UV. So first element into second element, X into V, second element into first element. So just the letter is different. Remaining everything is what? Same. That's why I leave the subdivision 1 to you. You can check it. Next is subdivision number 2. So in subdivision 2, if our capital R is a relation on the set of positive integers such that a comma b belongs to R if and only if AB is a perfect square. So you should understand first what is the relation. So a comma b in R if and only if AB is what? It's a perfect square. Okay. Now, if I prove if the relation R is reflexive means a comma A belongs to what? R. So if okay, to prove a comma A belongs to R, what I need to prove? A into A is a perfect square. That is what? A square is a perfect square. Okay, so the question is whether a square is a perfect square or yes. So since a square is a perfect square, so and hence you can write a square equal to what? A into a. So a into a is a perfect square. So if a into a is a perfect square, you can write what? A comma a belongs to what? Capital R. So and hence R is reflexive. Second one, A related to B. I should assume, I should prove what? B related to A. If A related to B implies from the definition of the problem in the problem, AB is a perfect square. AB is a perfect square. Now B is also perfect square. So and hence B is related to A, and hence R is what? Symmetry. So transitive, A is related to B. So and hence AB is a perfect square. So that I'll take AB equal to some x square. B is related to C. So and hence BC equal to what? Y square. BC is a perfect square. That's why I'll take y square. So now multiply the equation 1 and 2. So A, B square, C is equal to what? X square, Y square. I keep A and C in the left hand side. So remaining thing I'll go into the right hand side. So x square, Y square by what? B square, or xy by what? B square. So this is it's not percent square, perfect square. So and hence A is what? Related to C. So R is what? Transitive. Hence R is what? An equivalence relation. So next problem. Here also there are two subdivisions. If capital R is a relation on the set of positive integers such that A comma B is an element of R if and only if A square plus B is even number. Prove that R is an equivalence relation. Okay, so this is the first question. First we will discuss this one. So A comma B belongs to R if and only if A square plus B is even. So to prove R is reflexive, what I need to prove? A comma A belongs to what? R. When we can show A comma A belongs to R, because when we can show A comma A belongs to R, if A square plus A is an even number. So that's why I'll calculate what? A square plus A. A square plus A is equal to what? A into A plus 1. But we know that A and A plus 1 are consecutive positive integers. So any two consecutive positive integer is what? If you multiply, you'll get an even number. So A square plus A equal to, you'll get what? Even number. Okay, that's why A is related to what? A. Okay, and hence R is reflexive. Next, symmetry. For symmetry, A comma B belongs to what? R. I need to prove B comma A belongs to R. So A comma B belongs to R implies A square plus B is what? Even. So if A square plus B is even, then both A and B are odd, or both A and B are what? Even number. So because A square plus B is even, because square of an odd number is what? Odd. Similarly, square of an even number is what? Even number. Okay. So if both of them are A and B are odd, A square plus B is what? Even. Similarly, A and B are even, A square plus B is what? Even. So if A square plus B even, then A and B are what? Both of them are either odd number or even number. Okay. So in either case, in either case means if A and B are even or A and B are odd. So in both cases, you can check it. B square plus A is also what? Even. So and hence B comma A belongs to capital R. So that is the meaning of what is the meaning? B is related to A. So and hence R is reflexive. Sorry, R is symmetric. Next, transitive. When A comma B comma C are even. Okay, there are two cases. All of them are even. All of them are what? Odd. ABC is even. Then a square plus b, that is a is related to b. This is what b is related to c. So if a b c is even, now a square plus b is what? Even. B square plus c is what? That is also even. So and hence a square plus c is also what? So even number. Similarly, ABC is odd. This is what? A is related to B. This is B is related to C. So and hence A square plus B is, from this we have what? A square plus B is even number. Similarly, B square plus C is what? Even number. Okay. So A comma B related to R implies what? A square plus B is even. B comma C is related to R implies what? B square plus C is even. So from this we know that a square plus c is also what? A square plus c is also an even number. Okay. Now, or sometimes we can tell like this. Okay, but this is enough. But if you want to tell, okay, if you want to write, okay, also you can write like this: a square plus b even. Okay, first case a b c are even. So a square plus b is even. Now you can write what? A square plus b is even means you can write some 2 into what? M. Okay, or 2 into m. Similarly, b square plus c is even. Now you can write what? B square plus c is equal to what? 2n. So if you add these two, what you'll get? A square plus b plus b square. But if you add this, you cannot get what? You cannot get a square plus, I think I need to put what? A square plus c then. Okay. So b square plus c, which is equal to 2m, 2 into what? M plus n. You can write like this. So I'll keep a square plus c left side. Right side is what? 2 into m plus n minus b into minus b square. B square. Then you can write this is what? 2 into m plus n minus, if you take b common, b into what? B plus 1. Okay, minus. So we know that as a consecutive integers, this is an even number. So this is also what? Even number. So even number minus even number, you'll get what? Again an even number. So and hence a square plus c is what? Even number. Okay. So in this way also you can say that like this. Similarly, when a, b, c are odd, you can give the same proof. But here they are written directly. Okay. You can, if you want to write elaborately, you can write. So and hence R is what? Transitive. And hence R is equivalence relation. Okay, subdivision 2. So what is subdivision 2? If R is the relation on the set of integers such that a comma b belongs to capital R, if and only if 3a plus 4b equal to 7n for some integer n. Prove that R is an equivalence relation. So I will write here a is related to b, a comma b belongs to R, if and only if 3a plus 4b equal to 7n. Okay, 3a plus 4b equal to 7n for some integer n. For some integer n. So I want to prove it is first reflexive. So to prove it is reflexive, I want to prove what? A is related to A. So instead of proving a comma a belongs to R, I should prove what? 3a plus 4a equal to what? 7a. I can check it here. Okay, 3a plus 4a equal to what? 7a. So this is of the form what? Like this, 3a plus 4. Here have b. So if it here also a means what? A, it is equal to multiple of what? 7. So and hence you can say a is related to what? A. And hence R is what? Reflexive. So next I need to assume what? For symmetry, A is related to B. So this implies 3A plus 4B equal to 7N. So now I am going to calculate 3B plus 4A. 3B plus 4A, because I want to prove what? B is related to A. So 3A plus 4B equal to 7A plus 7B minus 3A minus of 3A plus what? 4B. So what you'll get here? This one is what? 7A minus 3A is what? 4A. 7B minus 4B is what? 3B. Okay. These two are equal. So now 7 into A plus B minus what is 3A plus 4B? 7N. So which is equal to 7 is common. So A plus B minus N. So we know that A, B, N are what? Everything integers. Okay. So A, B, and N are integers. So that's why A plus B minus N is also what? Integer. It is a multiple of 7. So and hence this implies we can say that B comma A is also related, and hence it is what? Symmetry. So the last one, transitive. Let A comma B in R and B comma C in R. I should prove A comma C in R. So A comma B in R implies 3A plus 4B equal to 7M. B comma C in R implies what? 3B plus 4C is equal to 7N. So now I am going to add these two. Okay. So 3A plus 4B. Okay. 3A plus 4B plus and 3B plus 4C. 3B plus 4C equal to 7M plus 7N. So 7 into M plus N. So finally 3A plus 4C is equal to 7 into M plus N, 7B, so minus B. So this is again what? M plus N minus B is an integer. So this implies A is related to C. 3A plus 4C is equal to 7 into M plus N minus B, where M plus N minus B is an integer. So A comma C are related, and hence it is a transitive, and hence it is what? Equivalence relation. So next column, just I'll quickly tell this one. Okay. So here the relation is defined by here x1, y1 are related to what? x2, y2, if and only if x1 equal to x2. I'll write here x1, y1, x1 comma y1 is related to x2 comma y2 if and only if, but here there is no role for y1 and y2 actually. So x1 equal to x2. Okay. So this is a relation. Show that R is what? Equivalence relation. So we know that x is equal to x. Okay, x is equal to x. So x is equal to x implies. So here x1 equal to x2 implies what? X1 comma some y1 are related to what? This x2 comma what? Y2. So x comma y, x is equal to x implies so x comma some y, I'll write related to the same x here. Okay. So here we have this x, I'll write x comma y, and hence R is what? Reflexive. So you can this x1 is here, this x2 is what? Here. Similarly, this x is here, This x is what here, and you can write whatever you need here, because I need here what y. Here also I'll put what y. So then only I can show what it is what reflexive. Next, for symmetric, x1 comma y1 is related to x2 comma y2. So implies x1 equal to what? x2. Implies x2 is equal to x1. x2 equal to x1, and you can write first here x2 and then here first x1. So here whatever you need, okay, y2, here what? y1. So this implies, sorry, here I can't put equal to, here I should put what? Relate, they are related by definition, So this implies R is what? Symmetry. R is symmetric. The third one I will show you in the PDF. For transitive, x1 comma y1 related to x2 comma y2, and x2 comma y2 is related to what? x3 comma y3. So from this, from the definition of, we have what? x1 equal to what? First coordinate equal to first coordinate, x1 equal to x2. From this, first coordinate equal to what? First coordinate, x2 is equal to x3. Now x1 equal to x2, x2 is equal to x3 implies what? x1 equal to x3. If it is x1 equal to x3, you can write here x1, here x3, and here you can put what? y1, here you can put what? y3. So hence R is what? Transitive. So the next problem, define R on the relation R on R square. R square is a two-dimensional plane other than the element 0, 0 by x1 comma y1 related to x2 comma y2 if and only if there exists some alpha, non-zero alpha in R, okay, such that x1 is equal to alpha into x2. That is the first element is equal to some alpha into alpha is what? A real number. This R is what? Real number. This R is a relation. This R is what? Real number. This R square is what? Two-dimensional plane. Okay, that's why they are written like this. I think you know the difference between this R and this R. This R. These two are same. This is R. This is R square. This is the relation R. Okay. Now x1. These two ordered pairs are related if and only if the first element is equal to some real number into the first element. Similarly, the second element is equal to some real number into what? y2, second element. So we should show that R is an equivalence relation. So first I should prove x comma y related to what? X comma y. So for this, how to prove this one? X is equal to some 1 into x. Okay, wow. So x is equal to some 1 into x. Here alpha is what? 1. So y is equal to some 1 into y. So this x is here. You should write this x is what? Here. This x is here. Okay, x1 is here, x2 is here. Similarly, y, the second element, y1 equal to y, alpha into y2 means what? This y1 is here, this y2 is here. Second element. So this y is I'm writing here, this y I'll write here. So hence R is reflexive. So next, I'll take, you can take x1 comma y1 also you can take. Okay, there is no need to take x comma y. Okay, well, I'll write x1 comma y1. x1 comma y1 is related to what? x2 comma y2. So this implies x1 equal to some alpha into what? x2, and y1 equal to some alpha into what? y2. So this implies x2 is equal to 1 by alpha. Okay, 1 by alpha into what? X1, and y2 is equal to 1 by alpha into y1. So alpha is a real number. So x2 is equal to, I'll take 1 by alpha is alpha dash. So 1 by alpha is a real number. Now 1 by alpha is also a real number. So hence alpha dash is what? Real number. So y2 is equal to what? Some alpha dash into y1. So it is written here. Okay, now this implies this is first element x2. Okay, and this is what? Second element x2 comma x1 is related to this is the first element y2 comma what? Y1, and hence the relation is what? Symmetric. The reason is what? The alpha dash is equal to 1 by alpha is a real number. Okay, next the third one, transitive. Maybe I will explain using this PDF. Assume x1 comma y1 related to x2 comma y2, and x2 comma y2 is related to what? X3 comma y3. So from this, what you have? X1 equal to some alpha into x2, and y1 equal to what? Some alpha into y2. From this, we have x2 is equal to alpha dash. Okay, alpha dash into because alpha should be what? A real number. So instead of, I'll take what? Alpha dash is equal to what? Alpha dash x2 is equal to alpha dash into x3, and y2 is equal to what? Alpha dash into y3. Now x1, I'll start from this x1. X1 equal to alpha into x2 is equal to alpha. What is x2? Alpha dash into x3. So now I'll take alpha into alpha dash is equal to some other real number alpha 2 into x3. Similarly, I'll start from y1. What is y1? Alpha into y2 equal to alpha. What is y2? Alpha dash y3. So alpha into alpha dash is both of them are real number. So product is again a real number alpha 2 into y3. So now x1 equal to alpha 2 into x3. So and similarly y1 equal to what? Alpha 2 into y3. So this is the first coordinate x1. Okay, x3 is what? First coordinate here, and then y1 is the first coordinate here, and y3 is what? Second coordinate here. So from the definition, I can write like this: x1 comma y1 related to x3 comma y3. Okay, so I think from this x1 equal to alpha x2, y1 equal to alpha y2 implies what? X1 comma y1 is related to what? X2 comma y2. So same thing I am doing here. So x1 equal to alpha 2 x3, y1 equal to what? Alpha 2 y3 implies x1 comma y1 related to what? X3 comma y3. So and hence R is transitive, and hence R is an equivalence relation. So there are some practice problem. Okay, 1, 2, 3. You can do it and then verify it. I'll check the time. Maybe I'll take maybe 5 more minutes. I can take. So quickly I'll finish it. Yeah, this problem. So if you have any doubts, you can ask to me in this problem. Determine whether the relation R on the set of all integers is reflexive, symmetric, antisymmetric, or transitive, where A is related to B if and only if first one, A not equal to B. So A related to B if and only if A not equal to B. First we will discuss this one. There are here 8 problems are here. So actually A not equal to A is actually what? Not true. Because A not equal to B is a relation. So A not equal to A is what? Is not true. And hence actually to prove R is reflexive, what I need to prove? A not equal to A. But A not equal to E is not true, and hence R is what? Not reflexive. So second one, symmetry. A is related to B. That means what? A not equal to B implies B not equal to A. And hence A is related to B implies what? B is also what? Related to what? A. And hence R is symmetry. So A related to B and B related to C. So that is what A not equal to B and B not equal to C does not imply what? A not equal to C. So you can take this is a 2, this is 3. Okay, 2 not equal to 3. Okay, 3. You can take C is also what? A. Okay, C equal to 2. So then these two are not equal, but this does not imply what? A not equal to what? C. So and hence R is what? Not transitive. It is symmetry. But what about anti-symmetry? For anti-symmetry, okay, for two different elements I should take. Okay, so okay, for two different elements I should take. Okay, okay, two different elements. X is not equal to y. Suppose if I take x is not equal to y, x is related to what? X comma y are what? They are related. I should prove x y comma x is x should not be in what? R. But here, okay, the relation is what? Here not equal. So x is x comma y is related. This implies what is the meaning of this? X is what? Not equal to y. Okay, but this implies y is also what? Not equal to x. So y not equal to x means what? Y comma x in what? R. Okay, but I need to prove what? Y comma x should not be in what? R. Okay, but here y comma x is in R. That's why this relation is what? Not antisymmetry. Okay, next. AB greater than or equal to 0. Okay, so first one, to prove R is reflexive, A into A is what? Greater than or equal to 0. A into A is what? A square. A square is greater than or equal to 0. So R is what? Reflexive. Next, A is related to B. A related to B implies what? AB is greater than or equal to 0. Implies BA is also greater than or equal to 0. And hence B is related to what? A, and hence R is what? Symmetry. Third one, it is not transitive. Why it is not transitive? A, okay, this is A, this is B. Product is what? Greater than or equal to 0. This is A, this is B. Again, product is what? Greater than or equal to 0. But this is A, this is B. Actually, B is 0, 0. C is what? Minus 3. So, if you take a product, 2 to minus 3 is what? Strictly less than 0. So that's why it is not transitive. It is reflexive and symmetry, not transitive. So same thing again for whether it is antisymmetry question. So AB greater than or equal to 0. Okay, so AB greater than or equal to 0 means I'll take two different elements, A comma B, two distinct elements. X is related to what? Or A is related to what? B. A related to B. A comma, that means what? A comma B belongs to R. Implies what? A B greater than or equal to what? 0. Okay, I need to prove what? B comma A should not be in R. Should not be in R. Two distinct elements. Okay? I should assume this. Whenever this is true, I should prove this. But AB greater than or equal to 0 implies what? BA is also what? Sorry, B into A. B into A is also what? Greater than or equal to 0. Automatically you can say what? B comma A is belongs to what? R. But I should prove what? It is not in R. So, and hence this relation is also what? It's not antisymmetric. Okay. Second one, AB greater than or equal to 0. Next, AB greater than or equal to 1. Third subdivision. So AB greater than or equal to 1. To prove it is reflexive, A into A greater than or equal to 1. So that means what? A square is what? Greater than or equal to 1. But here you can see R is what? Your set of all integers. Set of all integers, set of all integers means either positive integer or negative integers, or it may contains what? 0. So a square greater than to 1 need not be true, because actually reflexive means what? A is related to A for every A. Okay, well, suppose if A is 0 now, then this inequality is not satisfied. But the remaining element is satisfied. But reflexive means what? A is related to A for every A belongs to in that set. Okay, here the set is what? Set of all integers. So that's why A square is greater than to A is need not be true. Okay, since A may be 0. So therefore R is what? Not reflexive. Next, A related to B. That means what? AB greater than to 1. AB greater than to 1 implies what? BA greater than to 1. So, and hence R is what? Symmetry. Third one, transitive. So, transitive you should assume what? A is related to B. And A is related to B implies what? AB greater than to 1. B is related to C implies what? BC is greater than to 1. So, this implies, so in this case, okay, either ABC or everything or what? Greater than 0, or everything what? Less than 0. So if everything positive na, okay, so you'll get greater than to 1. Everything less than also, you'll get what? Greater than to 1. You can check it. Okay, now if ABC is first case, if ABC is what? Greater than 0. Okay, ABC is what? Greater than 0. So now the least value of A equal to the least value of B equal to least value of C is what? 1. So that's why A into C is what? Either 1 or greater than 1 strictly. That's why AC is what? Greater than equal to what? 1. Similarly, the next case, what is the next case? If all ABC is what? Less than 0. So less than 0, the greatest value of A and the greatest value of B, greatest value of C is what? -1. So in this case, A into C is also greater than to 1, because A is -2. A is what? -2. C is what? -5. So -2 into -5 is what? 10. So that is what? Greater than equal to what? 1. So if suppose if I take A is -1, C is -5, because that is also what? Less than 0, -5. Then both, okay, suppose both of them are -1 now, you will get what? Equality. A into C is what? Equal to 1. In the remaining cases, you will get what? AC is strictly greater than what? 1. So in both cases, when ABC are greater than 0, we have what? AC greater than 1. If all ABC are less than 0, you'll get what? AC is greater than 1. And hence R is what? Transitive. And hence finally we proved it is what? Symmetry and what? Transitive. It is not what? Reflexive. Okay, next, fourth one. A is multiple of B. A is multiple of B, you can easily prove. So to prove it is reflexive, A is a multiple of A. Okay, A is a multiple of A is correct. So that's why R is what? Reflexive. Next, A is multiple of B, but symmetry will not, it is not symmetry. If A is a multiple of B, then you cannot say what? B is also is a multiple of what? A in general. So, but it is anti-symmetric. Why it is anti-symmetric? If it is, if A is a multiple of B and B is a multiple of A, then you can say it is what? A equal to what? B. So that's why it is anti-symmetric. And then transitive, when A is what? Multiple of B and B is a multiple of C, then automatically A is what? Multiple of C. And hence R is what? Transitive. So thus R is reflexive, anti-symmetric, transitive. Fourth one is over. Fifth one. So A is congruent to B mod 7. So already I proved A is congruent to B mod M in general, or X is congruent to Y mod M. Okay, so now here this is a particular case of that problem. You can see here fifth one. Okay, so for this I should prove uh, a is congruent to a. I should prove. So a minus a equal to what? 0. Okay, 0 is what? It's a multiple of what? 7. So okay, so I think this problem is already we discussed. Instead of 7, I even put general m. I proved. Okay, now next one, sixth one, modulus of a minus b equal to 1. This relation, modulus of a minus b equal to 1. So R is actually not reflexive. Why it is not reflexive means modulus of a minus 1 is a minus a. Modulus of a minus a equal to 0 actually. So that's why it is not equal to 1. Okay, wow. So therefore R is what? Not reflexive. Next, a related to b implies what? Modulus of a minus b equal to 1 implies what? Modulus of b minus a is also 1. And hence it is what? R is symmetric. So next, transitive, modulus of a minus b equal to 1. And also you should assume what? Modulus of b minus c equal to 1. So modulus of a minus b equal to 1 na, so a minus b equal to what? Either 1 or minus 1. Similarly, modulus of b minus c equal to 1 implies what? B minus c is what? Either 1 or minus 1. Now, if we add both 1 and 2, if we add 1 and 2, b gets cancelled. Okay, wow. So a minus c is equal to, if both of them are 1 na, you'll get 2. Both of them are minus 1 na, you'll get minus 2. If one is 1, another one is minus 1 na, you'll get 0. So there are 3 combination. One is what? 2 or minus 2 or 0. Okay, wow. That's why plus or minus 2 or 0. So if I put modulus, okay, wow, modulus of a minus c is what? You get 2 or what? 0 only will get. So that means modulus of a minus c is what? Not equal to 1. Okay, not equal to 1. So and hence it is not transitive, because we are assuming what? Modulus of a minus b equal to 1, modulus of b minus c equal to 1. I need to prove what? Modulus of a minus c equal to 1. But the modulus of a minus c is what? Not equal to 1. And hence it is not transitive. And hence also it is not reflexive, but it is only what? Symmetry. Sixth one is over. Seventh one, a equal to b square. A equal to b square. Here a equal to a square, because to prove R is reflexive, I need to prove what? A equal to a square. So a equal to a square is not true for all integers. So that's why it is what? It's not reflexive. Next, it is actually is not symmetry. So we'll check it whether it is antisymmetric. So antisymmetric, whenever A related to B, what do you mean by A related to B? A equal to B square, and B related to A. B related to A implies what? B equal to A square. Okay, so then A equal to B. So here A equal to A and B are what? Either 0 or A and B are equal to what? 1. So for the remaining case, this is not true. But in the antisymmetry definition says what? Actually, antisymmetry definition says whenever A related to B and B related to A. Okay, wow. So in this case, A equal to B. I'll show you the definition of antisymmetry again. Maybe yes, here you can see there are two definitions for antisymmetric. Okay, relation R on a set A should be antisymmetric whenever A comma B and B comma A in R, then A equal to B. So this is the the definition of antisymmetric. Okay, so using this definition, so suppose if you have A is related to B, that is A equal to B square and B equal to A square, then A equal to B is for what? For 0 and what? 1. Next, A related to B and B related to C does not imply what? Because A equal to B square, B equal to C square does not imply what? A equal to what? C square. And hence R is what? Not transitive. The last one. The last one is A greater than or equal to B square. A greater than or equal to B square. So actually A greater than or equal to A square is not true for all integers. So that's why R is what? Not reflexive. And also it is not symmetric. Okay. And it's anti-symmetric. Whenever A related to B, that means what? A greater than or equal to B square. And B related to what? A. That means B greater than or equal to what? A square. Imply A equal to B. So both of them are what? Same. So and hence R is anti-symmetric. So but R is transitive. Yes. A is greater than or equal to B square. And B is greater than or equal to C square. And hence A is greater than or equal to what? C square. Because A greater than or equal to B square, but B square is what? Strictly greater than what? B, but B is greater than or equal to C square, and hence A is greater than or equal to C square. So and hence R is transitive. So it is not reflexive, but it is what? Anti-symmetric and transitive. So okay, I'll stop here. The remaining problems we will discuss in the next class. If you have any doubt, you can ask to me. Otherwise, we'll discuss the remaining problem tomorrow class. Thank you.